This is a lesson on 4.1b, the reciprocal function in translations. If you can remember from the previous section, we talked about inverse variation, and we used the equation y equals k over x. Well, for today, we're going to take the most basic inverse variation. This occurs when k is equal to 1. When k equals 1, we have this function y equals 1 over x. We're going to call this a reciprocal function, and this is actually going to be the parent function, the most basic function of all inverse variations. So we want to be able to graph this parent function, and to do so, we're going to first come up with some points. So we're essentially going to take all of these x values in this table, and we're going to substitute it into this function, y equals 1 over x. So when x is -3, y is 1 divided by -3. When x is -2, we have 1 divided by -2. When x is -1, y is 1 divided by -1, which is simply -1. When x is -1/2, we have an interesting case. We have 1 divided by -1/2, which actually converts to simply -2. So y is -2. When x is -1/3, y is -3. We have another interesting thing happening when x is equal to 0. We know if I were to type 1 divided by 0 into a calculator, we would get an error. This is because we cannot divide by 0. So for our purposes, we're going to put does not exist. Moving down the table, when x is 1/3, y is 3. When x is 1/2, y is 2. When x is 1, y is 1. When x is 2, y is 1/2. And when x is 3, y is 1/3. So now that we have generated some points, we are going to plot them on our graph. Let's start with our first point, -3, -1/3. Move on to -2, -1/2, -1, -1, -1/2, -2, -1/3, -3. Now, having plotted these first 5 points, we could see a graph starting to take shape here. As you graph these points, you can see that the function is essentially going right next to our axes, both the x-axis and the y-axis, but it doesn't actually touch it. Let's continue plotting the remaining points to see what the second half of the graph looks like. Again, there's no point at x equals 0, so we're going to move on to x equals 1/3. When x is 1/3, y is 3. When x is 1/2, y is 2. When x is 1, y is 1. When x is 2, y is 1/2. And when x is 3, y is 1/3. We see we have a similar shape, the shape of a boomerang, but this one is now located in the first quadrant. Again, it's essentially riding along both the y-axis and the x-axis, but never touching. So this is the shape of the parent function. Again, just so we're clear, the parent function is simply the red lines, not necessarily the purple line. The purple is just giving it shape to it, allowing us to draw it easier. Now, those purple lines do have a special name. They are called asymptotes. We'll define that now. Asymptotes are lines a function approaches but does not touch. And you can see that definition in this case. The two purple lines are lines the function is approaching but never actually touches. Now, in this case, we already said the function is approaching the y-axis, which we call the vertical asymptote. The y-axis is the vertical asymptote in this case, which gives us the equation x equals 0. This vertical dashed line in blue is the equation x equals 0. The horizontal asymptote is this x-axis, and that has the equation y equals 0. It's important to identify the asymptotes, both the horizontal and the vertical, because it'll allow us to graph these reciprocal functions. So now let's look at a reciprocal function with slight differences. In this case, we want to graph the function y equals 5 over x. Well, comparing that to the parent function of y equals 1 over x, we clearly can see this 5 is going to transform our graph. This graph is going to have a vertical stretch by a factor of 5. Now, if you recall from earlier sections when working with parent functions, we always like to look at specific points. From your parent function, you want to be able to remember the following 2 points: the ordered pair 1, 1, and the ordered pair negative 1, negative 1. So if we're trying to graph y equals 5 over x, we want to transform those 2 points from the parent function we would transform it for our new function. Well, if there's a vertical stretch by a factor of 5, we're simply going to take the y coordinates and multiply them by 5. So we have the 2 new pairs of 1, 5 and negative 1, negative 5. Let's go ahead and plot those. 1, 5, 1, 2, 3, 4, 5, and negative 1, negative 5. Now, right now, it doesn't look like we have a lot to graph this function, so we also want to make sure we consider the asymptotes. Now, if you recall from the parent function, the asymptotes were simply the x and y axes. Well, with this new function, there was no movement left, right, up, nor down. Since there's no movement horizontally or vertically, there's no change in our asymptotes. That means our horizontal asymptote will remain y equals 0. Our vertical asymptote is going to remain x equals 0. So let's go ahead and plot this. Now, when I plot my asymptotes, I'm simply going to plot dashed lines. Again, these are not part of our final graph, but it helps us graph it. All right? We know, based on the shape of the parent function, we should have a boomerang in the first quadrant and a boomerang in the third quadrant. So to finish off this graph, I'm going to draw a rough sketch in my first quadrant and a rough sketch in my second quadrant. And there is the function y equals 5 over x. So let's look at another one with more transformations. And in this case, we want to look at the function y equals 1 over x minus 3 plus 2. Well, again, we want to compare it to the parent function y equals 1 over x. The plus 2 on the tail end of our function tells us we're going to move this up 2 units. The x minus 3 is going to tell us we're going to move right 3 units. Remember, with the horizontal translation, we always do the opposite of what we see. Now, these translations are really moving the function, but it's also moving the asymptotes. So remember, originally, we would have a vertical asymptote at x equals 0. But because of our horizontal translation, our new vertical asymptote is going to become x equals 3. I can plot that right now. Similarly, for the horizontal asymptote, the original horizontal asymptote was y equals 0. Since we are moving this up 2 units, this new horizontal asymptote is going to become y equals 2. And I can go ahead and plot that again with a horizontal dashed line. Now, looking at again the function we're working with, there is no stretch nor compression, nor is there a reflection. So if I go back to the parent function, it's good to again remember those 2 points. 1, 1, negative 1, negative 1. Now notice how those 2 points are essentially 1 unit by 1 unit from your origin, or the intersection of the asymptotes. We can use that concept for this function right here. We have to look at the new intersection of the asymptotes and simply go 1 by 1 in the first quadrant, in our first new quadrant, if you want to call it, and 1 by 1 to get into the third quadrant of our new, the new third quadrant, we should call it. From there, we can just draw a rough sketch, knowing that we're going to have 2 boomerangs, and we have the graph y equals 1 over x minus 3 plus 2. Now, if you feel comfortable with this now, you should be okay, but we're going to walk through one more in case you need another one. So here we have y equals 1 over x plus 5 minus 6. Again, the first trick is to identify the translations. X plus 5 tells us we're moving left 5 units. Minus 6 tells us we're moving down 6 units. Those translations affect the asymptotes. Because we move left 5 units, the vertical asymptote becomes x equals negative 5. We'll plot that in here. And because we're moving down 6 units, the horizontal asymptote is y equals negative 6. We can plot that right here. Now again, because there's no stretch, there's no a value besides being just 1 there, we can use the trick of going 1 by 1 from our new intersection point from our asymptote. So here's our intersection point. 1 by 1 in the new first quadrant, 1 by 1 in the new third quadrant, generates 2 points. And you can draw a rough sketch of your 2 boomerangs.